Introduction to our speaker today. Welcome to the Data Science Seminar Series at the University of San Francisco, sponsored by the Data Institute. Data Institute is the umbrella organization for all things data science at the University of San Francisco. Our speaker for today is Mr. Kunal Sonalkar. Kunal is a data scientist at Nordstrom, a fashion retail company. His primary responsibilities involve enhancing search retrieval experience and providing personalized product recommendations to online customers. He holds a master's degree in computer science and engineering from the University of Florida. His topic for today is LORA, low rank adoption for efficient language model fine-tuning. So let's give an applause to our speaker for today.
Thank you. Is everyone able to hear me? Okay. So before we get started, is everyone familiar with the transformers architecture, transformers model, that's that? Okay. Awesome. And how many of you have heard about LORA? Okay. Oh, that's good. Okay. We'll have a good conversation. Awesome. So let's get started. Oh, and congratulations on the graduation. I heard you are graduating next week, so this is great. Okay, so LORA is basically low rank adaptation, and this was a paper which came out of Microsoft research, and this was essentially targeted to fine-tune the large language models or the foundation models for specific use cases, and we'll sort of get into that a little bit. So the agenda I have today about this is we'll start with some transformers, quick introduction, the architecture, and the parameters which are involved in transformers. Then we'll sort of move to what is fine-tuning, then motivation for the parameter efficient fine-tuning, then what is low-rank adaptation, evaluation of those models, then some implementation details, and then what would be the potential limitations and like the future directions of LORA as such. Okay, so starting with the basics of transformers. So the standard definition of transformer is it's a neural network that learns context and does meaning by tracking relationships and sequential data like the words in the sentence. So just to give an example over here, I like this example. The animal did not cross the road because it was too tired, and the animal did not cross the road because it was too crowded. So over here, the context is super important. So if you notice, the it part in the first sentence is associated with animal, and in the second sentence, the it part is associated with the road. And transformers are really good at modeling and understanding the sequence relationships between the words, even if they are sort of far apart. So if you notice in the first sentence, the animal word is quite far apart from the it, and still it understands it pretty well. And the diagram or the screenshot below just indicates that the animal did not cross the street because it was too tired. So that it has the maximum weights assigned to the tired word. So that's what like the overall gist of transformers is, and it does through a technique called attention or self-attention, and that's how it works. So just to sort of give an introduction on that. So coming to the use cases, initially the way it started was it was used for sequence translation or machine translation per se. So you give an input in one language and you can get the output in the other language. So basically you had an input of text block, and then you were getting the output of the text block after the entire input was passed through the transformer. So then it was sort of thought out that, hey, if it's just about input and output of text, this can be extended to other use cases also. So if you see, you can sort of do sentiment analysis from the transformers, you can do summary generation, and then you can do question answer or like a chatbot sort of system, which now everyone knows that ChatGPT did with the question answer part. So this is all in a very similar format. You give an input of text and then you expect an output of text. And this model has sort of extended, replicated in variety of use cases. Okay. So just to sort of give a deeper dive on what this architecture looks like, it is filled with stacks of encoders and decoders. We don't need to sort of get into the nitty-gritty of what is encoder and what is decoder, but you sort of give an input, it goes through like these encoding layers, passes through the decoder, and then you get an output. And output is nothing but a probability of sequence of words, and then the word which has maximum probability gets outputted or generated in this case. So that's what this architecture looks like. If you sort of zoom into the encoder, it is nothing but a self-attention block with a feed-forward block. And in decoder, it is self-attention and then encoder-decoder attention and then feed-forward. So this is just the architecture from a deeper dive perspective. But overall, I think going forward with the LORA talk, I think it's good to remember that it is stacked with encoder and decoder layers, and you're sort of giving an input and you're getting an output. Okay, so another important part why we need to talk about LORA is the parameters which get involved in these transformer models. So if you notice, over here, I don't know if you're able to see the input, I think it has been cut out a little, but the animal did not cross, like this sentence gets passed into this transformer block, and then on top you sort of get the outputs. And this is just an example of what was the case during GPT-1 model. So you have like these 12 transformer blocks, and then the input keeps on getting passed through like block after the block, and then you get an output. There is also something called embedding matrix, and this embedding matrix, what it does is it sort of converts all of these tokens, or like the tokens of words, into a numbered vector-based format, and that's what embeddings are. So when you have to sort of pass this entire input to the transformer block, you get parameters associated with it. And these embedding layers have like 31 million parameters, attention layer has 27 million parameters, and then the feed-forward network of feed-forward neural network layers have 56 million parameters. So if you add them up, there are approximately like 116 million parameters which were there during part of GPT-1 training. And these parameters sort of get adjusted as the input flows through this transformer block, and then the loss gets back propagated through this transformer architecture. So you have to make sure that you are updating those 116 million parameters. And these number of parameters has consistently grown as transformer models have evolved. So I don't think like anyone even talks about 116 million parameters anymore. I think everyone is just talking in billions and billions of parameters. So this part becomes very challenging when you think about it. And we'll sort of get into like the challenges of that aspect as well. But this is how the parameters get calculated at every step of the way as the input flows through the transformer block. Okay, so where exactly are these parameters coming from? So you have model dimension, which is dimensionality of your input and output vectors. Then the word embeddings. Then you have position embedding parameters. So you also have, the position is important, as in like where the word is occurring in what sentence. We pass those parameters as well. Then you have the transformer parameters. There is something called attention heads, query, key, and value, the number of layers which are associated with attention heads, and then the feed-forward network, which is again part of transformer architecture. So every step of the way, you have a certain set of parameters which get trained. On the left-hand side, I just attached a screenshot of the GPT-3 models. So GPT-3 had 175 billion parameters, and it had 96 layers. The dimension was 12,096 attention heads, and then 128 dimension, the dimension of the heads. So Okay, so based on that, we have a lot of open source LLMs as well. Probably Grok is the one which has the most number of parameters, 314 billion. Then recently Llama 3 came out, so they have approximately 17 billion parameters. But I think these are like the ones, Mistral. BERT was one of the popular, I don't know how popular it is currently, but Mistral, Llama, Falcon and Grok. These are some of the very prominent open source LLMs. So starting with the life cycle, if we have to decide like how to train these LLMs or how to fine tune these LLMs, so this is what a typical life cycle looks like. You sort of specify the task, you move with an existing model, or you build your own. Like either you can just go with a standard, take it out of the box and use as it is. You can use GPT-based models, you can use Llama, or you can use Mistral, and you use it for your own task. Then there is prompt engineering. You can fine-tune that model if it's not working well for you right out of the box. Then there is evaluation cycle. Then there is optimize and deploy the model, and then there is build LLM-powered applications through it. So this is what like a typical life cycle looks like. And today we are primarily going to focus on the fine-tuning part of it. Like if you don't want to pay for a very big model as such, how can you fine-tune it in a parameter-efficient way? So that would be like the focus. Okay, so coming to the part, what is fine-tuning? So fine-tuning is basically when you sort of provide your pre-trained model a very special set of data, and that special set of data is restricted to a certain use case. So in the example, if you give symptoms like joint pain, skin rash, or sun sensitivity, and you have a base LLM model which does not have a lot of information about these symptoms, allergy symptoms. So it can give you a generic answer, but it might not be able to pinpoint you into what exactly is the root cause, or what can you interpret out of those symptoms. So this is where you sort of provide this allergy data to your previously trained model, and then that acts as a fine-tuned model. And then if you pass your symptoms like joint pain, skin rash, sun sensitivity, then it will be able to give you a much more defined answer, or it will be able to help you in a much better way. So that supplying of allergy data as an extra resource to this pre-trained model makes it like a fine-tuned model. So how can you actually get one fine-tuned model? So you have like this big web data. There are like these open source data sets like Common Crawl, where you train these big pre-trained models. And once you have that base LLM, you provide a knowledge base, and then you get a fine-tuned LLM. So the first step which you need to do is you need to take a pre-trained model, and then you need to load the weights, all of the weights which come with that pre-trained model. And then those weights are frozen, and then you sort of update the weights as you provide your explicit or the knowledge data set on which you want to fine tune. So normally this is generally done when your task is sort of narrow and your task is well defined, where you don't expect your general or pre-trained LLM to answer those specific questions. So like allergy data, or if you want help on insurance data or anything of that sort. This is when you don't expect the pre-trained model to be trained on that very narrow set of data, and this is where you can use fine-tuning. So in terms of fine-tuning, there are two types. One is full fine-tuning, and then the other is parameter-efficient fine-tuning. So in the full fine-tuning, what happens is when you load the pre-trained model, you have to sort of retrain it completely, and you update all the parameters based on your new data set which you're providing. So, and this becomes very expensive because if we are talking about like billions and billions of parameters, it's going to be very costly to load the entire data and then just update your billions of parameters. So another approach for that, or another alternative for that, is the parameter efficient fine tuning. So where you are going to sort of keep the pre-trained LLM as it is, but then you are going to add additional layers, or you are going to change only a few layers of that pre-trained LLM. So you are not going to change every parameter as such. You are just going to change either the last layer or the last two layers, or just you are going to add another additional layer which helps you in your use case. So in parameter efficient fine tuning, you will always have this fine tuned LLM, but then you are going to add this extra adapter per se, or extra additional parameter, which will be indicating that extra knowledge base which comes from providing that extra data set. Okay, so low rank adaptation, or LORA, is one of the techniques for doing parameter efficient fine tuning. And the way it works is you have your pre-trained weights, which are indicated in that black box, and then you have your change in weights. So whenever you want to update the weights, you're not going to track your original weights. You are going to track only the changes which you are making in your original weights. So if you notice over here in the purple, which is W dash, so W dash is nothing but addition of your pre-trained weights, and whatever changes which were made in your original weights are giving you the new fine-tuned weights. So this is like the basic equation on which LORA sort of develops. And the way this works is, so you have W, which is your original weights. Consider this like a 3x3 matrix. And then your change in weights is happening at, let's say, another 3x3 matrix. And then you finally get your fine-tuned weights. So what this is doing is, your delta W is the only part which is going to get tracked. Your pre-trained weights or the original weights are not going to change at all. They are going to be kept as it is. And this delta W is going to be broken down into two parts. So if you have a 3x3 matrix, this can be broken down into 3x1 and 1x3 matrix. So essentially, if you notice, instead of storing 9 parameters, you end up storing 6 parameters. And this is where that LORA comes in, where you are sort of decomposing this matrix, delta W, into a lower rank, and this lower rank is helping you save up on the storage costs and the compute costs, and avoiding sort of updating all of the weights together. Okay, so again, so this is more on the part of this rank sort of becomes a hyperparameter, or like a parameter to tune. Like either you can, so if you have a 3x3 matrix, you can use 1x3, 3x1, or you can use 2x3, 3x2 matrices, and you will still get the same result. So you can try out like different ranks which are there to decompose your changes in the weights which are happening. So this is sort of one of the very important parameters which comes out in the LORA framework as such. Because the more complex your task is, the higher your rank should be. So if it's a very simple task of, let's say determining a sentiment of a movie review as such, I think you can work with a very low rank of like, 8 or 10. But if it's a very complex task where you need to understand the context clearly and the data set is very intricate, then you need to increase your rank accordingly. Okay. So now, once you have sort of decided that you want to go with LORA, the way it works is, so on the left-hand side, if you look at how the inputs are flowing in a forward way, so your pre-trained weights are not going to change. You will sort of randomly initialize A and B matrices, and these A and B matrices, they don't get affected during the feed-forward cycle. But when there is the backward propagation of loss, your pre-trained weights are not going to get disturbed at all. but you are going to work only with your B matrix and your A matrix. So those are the only two matrices which are going to change if there is any change to begin with. So this is what this is how the weights get updated. So absolutely no change during the forward or like the forward flow of the inputs, but only the change happens in the A and B matrices when there is backward propagation of the loss. Okay, so once you sort of adopt that framework, you do see like there is a good or like a significant reduction in parameter size. So if there is a 7 billion model, if you use rank 1, you can literally come down to 167,000 parameters, and which is like a very big dip from a 7 billion parameter to like 167,000 parameters. So even if you go all the way up to 512 rank, you will get to 86 million parameters, and then the 7 billion would still, I mean, like you would end up saving still good amount of compute and costs if you come down from 7 billion to 86 million. The same thing goes for 13 billion and 70 billion. So just to sort of give you a comparison on how or like how significant these reduction in parameters could be if you decide to adopt that LORA. Okay, so once you have adopted that, or like you go for your training, there is one part which needs to be taken care of is the evaluation metrics. So primary metrics could be accuracy or the Rouge metric which is used for text generation, and then you can also have human evaluation. So GSM-8 is like a mathematical word problem database. So if you want to evaluate your models on mathematical problems, you can use that GSM-8K. And then there is post-processing where you can do like some qualitative analysis, and then human feedback is always there. But what generally has been observed is if you look at classification or generation, it's a little easier to beat GPT-4 if you go with LORA. But as the tasks sort of get more complicated, so the math part of it or like the coding part of it, it gets difficult to beat GPT-4. So again, I think one of the conclusions which we can draw from this would be like if you have simple tasks like quick classification or sentiment generation, it's quite simple to use LORA, and it's very cost efficient, compute efficient to use LORA. And then if you have very intricate tasks which you need to do at scale, then I think going with GPT-4 would be a better choice. Okay, so once we have done that, how do you actually serve LORA, or how do you actually provide, or how do you develop applications with this framework? So majority of the costs which sort of get associated with this would be the fine-tuning costs which we discussed, and then the other one would be model serving. So over here I'm taking example from a library called Lorax. I don't know, there is a company over here called Predibase, and that company maintains this open source library called Lorax. And it's a very useful library if someone is trying to sort of use these fine-tuned models fairly quickly. So we'll sort of get into the deeper dive of how this library operates and how you can actually serve these fine-tuned models and make applications out of it. Okay, so just to sort of get an intuition of how this deployment is working. So let's take like this code fragment, right? So over here you are sort of defining your 4 classes. Dog, bird, bear, fish, and every class has these associated functions with it. But if you notice, like eat and sleep are sort of common functions. So yes, I mean it's a well-functional code. There's nothing wrong with it. It's just that some functions are redundant, or like you don't need to create separate classes for these functions. So what you would want to do is you would want to have like one class of animal, and then eat and sleep can sort of be part of that class, and then you can use that class to define dog, for barking, and then bird for flying, and then fish for swimming. So this would be a much better or much more efficient way to have like one class as a constant thing over here, and then use that class as a base framework, and then build on top of that. So this is exactly the same way your model serving with LoRax is working out. So what happens is, let's say if you have a user and they are interested in trying out like one of the LLMs which you have fine-tuned. So all the light yellow colored symbols which you are seeing, they are pre-trained weights and they are not going to change. So we are going to keep those light yellow colored pre-trained weights as it is. What we are going to change is this adapter loading. So if the blue user comes, they can use the blue fine-tuned model or like the LoRa adapter, which you can see over here. If the red user comes, you can just swap that blue one and use the red one. If the green user comes, you can just swap those and then use the green one. So all in all, your yellow pre-trained weights are going to stay the same. And then you just keep on swapping as the different users come, and there are like different applications which they want to use. So if user 1 comes and if they want to use the summary generation, you are just going to expose them to the blue one. If the red one comes for like sentiment analysis, you take the red one, and the same thing goes for green. So this makes it much more efficient, and it makes it efficient to such an extent that literally using one GPU, you can actually serve around 25 fine-tuned models, and that is like something unheard of. Like, you know, you can actually get very good results out of those 25 fine-tuned large language models on a single GPU just by this adapter switching. And the good part is the library is open source, so everyone can like, you know, sort of play around with it. Okay, so coming to the part like what would be the challenges with LoRa. So one would be choosing the optimal rank, because that takes a lot of work in terms of getting that fine-tuned, like what would be the optimal rank and how complex your task is. So that would be one. Maintaining the model accuracy, these results are definitely promising, and you know, but there is sort of a performance ceiling associated with it. Then there is data dependency. So it's more like garbage in, garbage out. So the better your data is, the better your large language model would be. So it's very important or very necessary to sort of curate your data and get that right. So then the fine tuning will be able to help you in a much better way. And then the another part is like the constant model monitoring and maintenance. So I think that would be another challenge. But overall, I think this works in a pretty good way in terms of if you have to create a trade-off between the costs associated with it and the compute you save, and then getting the results for that. So it works out to be a pretty good trade-off. One last part I think which I can recommend over here is the LoRa paper and the LoRax library and the blog which is written by Redibase and Sebastian Raska's blog. I mean, so these blogs are like very useful if you want to understand how to fine-tune these models. LoRax library is open source and you can always use that. And then the LoRa paper has like good comparisons with how fine-tuned models work with GPT-based models. And the Redibase blog, which is there, that will also give you a very good idea in terms of how fine-tuned models are much better, you know, if not equal to the GPT-4o, which is recently released model. So yeah, that's about it from my side. Like if any questions, we can have a Q&A.
Any questions? We have mics over there. Right. So I have one question.
Yeah.
The decomposition of those parameters into those matrices, does that change based on the domain? Like
Yes.
say for example, an insurance company or a healthcare, does that matter how you're decomposing or which level of rank you're using?
Yes, so generally the way it works is the more complex your task is, the higher your rank should be. And sort of it will work, it has to be sort of an empirical experiment as well. You might have to try out like certain ranks for that decomposition before you actually fix on, okay, this is the rank which I'm going to go with. So yes, I mean it's completely changeable depending on your use case.
But then, how many iterations are good enough to say, hey, this is my my final set to use for my production environment?
Okay, so the blogs which I read or like the videos which I have seen across, like around 20,000 iterations were used to sort of fixate on a certain rank as such. But I think again it would depend on a use case also.
I have a question about so the allergy example. So we are using LORA to apply the external knowledge base about the more deeper knowledge about allergies. But I cannot draw the concrete example how we can construct a data set using this allergy data. Because so current input and output is like a chatting conversation. Like input is a user query and output is an answer.
Okay.
But the allergy data is just normal text like article about allergies. And how we can construct the data to fit into this chat.
Got it. So it depends on your use case. So if it's just a classification problem, right? Like you are going to give the symptoms, and at the end, if you're just going to get like one classification, okay, this is allergy, or this is flu, or this is something else. So that would be, you would have to train with a classification data set. You can literally do like a human curated data set where you would give symptoms, and then the classification label or the ground truth label would be like your the category of your allergy, and then this data gets passed into a pre-trained or the base model, and then you would sort of have to train based on this classification data set. The other part which you would want to do is it's just more like a question-answer based. So you would have to curate your data. You can literally just pass your articles, and then there is a technique called like mask language modeling. So based on that, you can sort of develop this model to predict the next generation model, the next generated words as such. So when you pass in your symptoms, it can actually generate like a description for you. So it just depends on your use case. Like if it's a classification base, you give the classification data set. If it's more like a question answering use case, you give like a chat based text. Yeah.
Thank you. And another question would be, so we also have a RAG and then context learning using
Yes.
the prompt engineering. So do you have any or practical criteria or boundary where you think, oh, this RAG or fine tuning is not going to work, and the prompt engineering is not going to work. We need a fine tuning like this situation.
Okay, so that's a great question. So there are a couple of different ways. So LORA is just one way to sort of infuse the external knowledge into your pre-trained models. So RAG is definitely one. And now there is a technique which is called RAFT, which is RAFT. So retrieval augmented fine tuning, where RAGs and fine tuning can sort of coexist together. So I think one part is it depends on the task which you have. I think prompt engineering and RAG-based tuning or like just RAG generation are pretty straightforward. Like you just have to provide external data sets, and then your pre-trained model does the work for you. So I think LORA would kick in only if these techniques are not working as you had expected or as you would like them to perform. So I think that would be an occasion where you can try out LORA. But yeah, that would be my answer. Thank you so much. Yes.
Any other questions? All right, let's give her another round of applause.
Thank you so much.